Right, this video we're going to talk about Born Haber cycles again. If you haven't already watched the video on the how to draw a Born Haber cycle for sodium chloride, then I suggest you go and watch that one first. So our learning objectives for today, we need to be able to describe and explain trends in lattice enthalpies, explain how covalent character can affect lattice enthalpies, and be able to use Born Haber cycles to calculate lattice enthalpies. So our definition, first of all, so there's two lattice enthalpies we need to be concerned with. There's the lattice enthalpy of formation, which is the standard enthalpy change when we're forming 1 mole of an ionic solid from its gaseous ions. And then there's the lattice enthalpy of dissociation, which is the opposite. So that's the standard enthalpy change when you're taking 1 mole of a solid ionic compound and you're dissociating that into its ions, into its gaseous ions. So those two are opposite to each other. So the value of those two for a specific compound is going to be the same, but they're going to have opposite signs. So the lattice enthalpy of formation is where we're forming bonds, so that's going to be exothermic, and the lattice enthalpy of dissociation is going to be endothermic because you are breaking apart of the ionic bond. So in terms of trends of lattice enthalpy, we need to be able to predict, if we're given two compounds, predict which one's going to have the highest lattice enthalpy. And in order to answer this question, we need to think about what lattice enthalpy is. So if we think it's easier if we think about lattice enthalpy of dissociation, but the arguments are the same for formation. So if it's lattice enthalpy of dissociation, we're trying to break that ionic bond. So we're trying to break that attraction between the positive and the negative ions. So the greater that attraction is, the more difficult it is to overcome that. So the greater the attraction between the positive and negative ions, the bigger the value for the lattice enthalpy. And that attraction is going to be higher if the charge on the ion is higher. So if you've got a negative ion and there's a +1 ion, that attraction is going to be weaker than if you've got a +2 ion. The size of the ion is also important. So if the ion's smaller, then the ions are going to be closer together, and therefore the attraction between them is going to be bigger. So we can wrap both of these arguments in one by talking about charge density. So if you've got a higher charge on the ion, you're going to have a higher charge density, and if you've got a smaller ion, it's going to have a smaller charge density. Now, we need to be careful in exam questions with this, because quite often people talk about the size of the atoms, or so we need to be very careful when we're writing answers to exam questions on these, that we make sure we're talking about ions. So there's something called the experimental lattice enthalpy, which is what we find from Born Haber cycle, and something called theoretical lattice enthalpy. So we need to just talk about the two differences here. So experimental values are those found using a Born Haber cycle. Now, people quite often find it confusing that they're called experimental values, because we tend to think of an experimental value as one where we've actually gone into a lab, we've done an experiment, and we've measured it and found it out that way. And that's not what we're doing here. We're using a Born Haber cycle to find that lattice enthalpy value. However, even though the value itself is not experimental because we're getting it from the Born Haber cycle, it's called that because all the other values in the cycle are experimental data. So we're deriving this value from experimental data, and we're using those with Hess's law to calculate our lattice enthalpy. So when we talk about theoretical values, they're calculated using computer modeling, and that's based on various assumptions. So it's based on the assumptions that there's 100% ionic bonding, that those ions are completely spherical, and that there's no polarization of those ions. So if the experimental and theoretical values are very similar, then that means we've got 100% ionic bonding. If the values are very different, then this means that there's some covalent character, and the larger the difference there is, the more covalent character there is. So we need to be able to think about why that covalent character happens. So at GCSE, we're very clearly defined these elements, when they react together, make covalent compounds, and these make ionic. But there's a bit of a grey area in between. So when we've got these ionic compounds, they're still ionic compounds, but they've got some covalent character, and we need to think about why that happens. So if you think about your positive and your negative ion, the positive ion is going to attract that electron density on the negative ion towards it. And if there's a great enough attraction, then you're going to get some overlap, because if it's really if it's really attracting that electron density, that electron cloud is going to come towards the positive ion, and you might get a bit of overlap there. And if you get a bit of overlap, then that's going to be covalent. So we don't call it a covalent bond because it's covalent character. It's still ionic bonding, it's just you've got a bit of covalent there. And covalent character is more likely when the positive ion's got a high charge density, so it's got a smaller ion with a higher charge, or the negative ion is easily polarizable. And what we mean by that is that that electron cloud is more easily distorted. And that happens when it's larger because the electrons are further away from the nucleus, so the attraction between the electrons and the nucleus is less. And it also happens when there's a higher charge because there's more electron density there that can be attracted towards the positive ion. So what does this actually look like? There's some better diagrams in your textbook, but this is my 3D paint job, which I apologize for the crudeness of. So the top diagram shows 100% ionic. There's no overlap there. So the positive ion and the negative ion are completely separate. There's then this kind of halfway house where the positive ion has dragged some of the electron density of the negative ion towards it. So it looks distorted. It's not completely spherical, but there's no overlap. So that does not have any covalent character. It's still ionic. And then the bottom one shows that the positive ion has managed to drag that electron density towards it, and there's some overlap. So some of that electron density is in between the two nuclei, between the positive ion and the negative ion. And because you've got that overlap, that means we've got some covalent character. Right, here's a typical exam question, where it's giving you some data. You need to draw a Born Haber cycle and use that Born Haber cycle to calculate the enthalpy of lattice dissociation in this case. When we're doing these questions, we need to be very clear whether it's dissociation or formation. Otherwise, you'll end up with the opposite, the same value, but the opposite opposite sign. It's difficult to do this on the computer screen, so I've made another video drawing out the Born Haber cycle. So take a look at that one. But this is what we need to do. So step one is draw the Born Haber cycle, include the enthalpy change values, and then once we've done that, we can calculate the missing value. But have a look at the video and that will explain it better. So this is the answer to that question. So you should come up with plus 2328 kilojoules per mole from that question. Right, now you've seen the demonstration, I want you to have a go at this exam question, which is very similar. So use the data in a table to calculate value for the lattice enthalpy of dissociation for silver chloride. So just follow the same method as on the other video. So the answer to this, so you should have found when you did that, was plus 905. The mistake students quite often make here, and you can see it's got CE equals no marks. So if you've written the formula as AgCl2, you get no marks for this question. It seems a bit harsh because we haven't done the charges on transition metal ions yet. However, silver chloride, you should know the formula of from our work on halogens and the silver nitrate test for the halide ions. Right, there's some extra practice. If you look in the thermodynamics booklet that I emailed out, have a go at the questions in task 5.